Welcome to This Explainer. Today, we're going to completely change the way you think about generative AI. For a long time, the dominant metaphor for AI image generation has been this idea of a magical paintbrush just producing art out of thin air. Well, we need to strip that metaphor away entirely. Here's a surprising fact to start us off. Despite producing award-winning, globally recognized art, these systems literally don't know what a paintbrush is. They don't understand color theory or human composition. What they do know is thermodynamics. In this explainer, we're going to look at diffusion models through the lens of the energetic paradigm. We'll reveal diffusion not as some mysterious act of creation, but as a highly structured, thermodynamic energy flow process. It's a governed system that meticulously recovers order from absolute noise.
Here's our agenda for today. We've got 6 sections: generation as structural recovery, forward diffusion, controlled corruption, path compression and training, reverse diffusion step-by-step repair, sampling paths and diagnostics, and finally, a general intelligence architecture.
All right, let's jump right into Section 1, generation as structural recovery.
So let's contrast two fundamentally different ideas. The outdated concept assumes the model constructs an image by drawing every part in a direct sequence. Much like a human painter, starting from a blank canvas and building an image brushstroke by brushstroke, or a mason building a house brick by brick. But the energetic paradigm's concept requires a total shift in our perspective. The system actually begins with a high-entropy reservoir, pure, undirected randomness. The generative process is really an energy flow problem, where the system navigates backward from disorder towards structure. Instead of building brick by brick, it operates more like a sculptor looking at a solid block of rough marble. It doesn't create pixels from nothing. It meticulously chisels away everything that isn't the sculpture, figuring out which part of a noisy state is the signal and which part is just random disturbance.
And looking at this, it perfectly illustrates our core thesis. We're treating generation not as creation, but as an energy flow problem, where a clean distribution is gradually degraded into noise. Now, at first glance, this might look like pure destruction, but it's fundamentally different. It's disciplined degradation. Uncontrolled destruction is like setting a photograph on fire. You can never get it back. Disciplined degradation, on the other hand, means the model meticulously destroys information in a mathematically tractable way. It carefully logs the state transitions precisely so that the reverse process can learn exactly how to recover that specific information later.
Moving right along to Section 2, forward diffusion, controlled corruption. The forward process flows through a very precise pipeline. We start with a clean image or data distribution. Then at each individual time step, we add a very small amount of controlled Gaussian noise. Think of these steps as entropy gates. The system is mathematically tracking exactly how information is being lost. And here's an incredible detail about the scale of this process. This descent into uncertainty usually happens over a precise sequence of around 1,000 distinct tracked steps. Finally, after passing through all these entropy gates, the original image completely disappears into an almost pure Gaussian distribution, which becomes our high-entropy noise reservoir. It's a perfectly measured, governed descent into total uncertainty.
Now, the crucial mechanism governing this entire descent is called the variance schedule. This isn't just some minor technical setting you can ignore. It's the absolute control policy for degradation. It acts as the master entropy gate, deciding exactly how quickly an image loses its structure. To picture this, imagine you're a sound engineer slowly turning up the background static on a radio dial. If you turn the static up too aggressively, the original song is instantly lost, and the reverse process trying to find the song becomes unstable and chaotic. But if you turn the static up too slowly, it takes ages to reach pure noise, making the training process terribly inefficient. So the variance schedule perfectly regulates this delicate balance between retained signal and injected disturbance to maintain system stability.
That brings us to Section 3, path compression in training.
If the model had to sequentially march through hundreds or thousands of forward steps every single time it trained on an image, the computational cost would be astronomical. It'd be completely unscalable. But the architecture uses a brilliant mathematical shortcut called the direct jump. Thankfully, Gaussian math is surprisingly cooperative, unlike a lot of things in software engineering. Because Gaussian distributions compose cleanly with one another, the system doesn't actually need to simulate every earlier step. The noise layers are mathematically predictable, which allows the system to randomly choose any time step and jump mathematically directly from the clean image to that specific noisy state. It's effectively skipping right to the end of the book. In the energetic paradigm, we call this path compression. It's an incredible production efficiency tool that preserves the exact distributional target while removing a massive amount of redundant computational cost.
Let's look at Section 4, reverse diffusion,
Step-by-step repair.
Here is where we initiate the core inversion sequence. We start with pure noise. The denoising network acts as a rigorous converter. It looks at the noisy state and performs noise estimation. It then applies a local correction, deciding what is removable noise and what is actually emerging structure. Keep in mind, this is not a single, inexplicable transformation. It's an iterative repair protocol. By repeating this process step by step, perhaps dozens or hundreds of times, it gradually constrains the uncertainty. It navigates through states of partial structure until we finally reach a stabilized form, the final image. The denoising network is not a creator mapping out a masterpiece. It's a learned repair mechanism strictly tasked with removing disturbance.
Figuring out the exact global law to completely reverse the noise all at once is mathematically intractable. It's simply an impossibly large problem. But the system uses a very clever trick during training. Because it already knows the original clean image, it can convert an impossible global generative objective into a perfectly trainable local repair signal. This is a profound shift in problem solving. The model doesn't have to optimize the entire universe of images at once. It just has to look at a noisy image, look at the specific time step, and predict the exact noise that was added in that one specific micro moment. Millions of these tiny, extremely easy local problems are solved, and enough of these local corrections chained together sequentially seamlessly recover the global structure.
Okay, Section 5, Sampling Paths and Diagnostics.
When we're actually executing the generation, we have to choose our routing, which we call sampling paths. On one side, we have DDPM. This classic approach uses many small stochastic steps. It actually adds a little bit of random noise back in at each step. This controlled randomness acts as a stabilizer, preventing early mistakes from rigidly locking the sample into a bad trajectory. Think of it like taking the long, highly stable scenic route to a destination. It offers fine-grained stability, but definitely at a higher computational cost. On the other side, we have DDIM. This path skips steps and uses fewer deterministic jumps. It preserves the learned correction field, but drastically lowers the cost, creating an explicit speed-quality trade-off. It's like taking a high-speed highway. You get there much faster, but larger jumps mean a single missed turn can accumulate massive errors. Ultimately, the goal is finding the lowest loss path for your specific use case.
Understanding this governed system is absolutely crucial for troubleshooting. When an image fails, a generic diagnosis just says, well, the output looks bad. But through the energetic paradigm, we can trace the exact mechanical origin of the failure across distinct layers. Did the model fail at noise estimation? Was our DDIM sampler skipping steps too aggressively? Was the variance schedule mismatched to the data? For example, if you see an AI-generated person with 6 fingers, that's often a local texture versus global coherence failure. The system perfectly denoised the local area of the hand, generating excellent skin and lighting, but it lost track of the macro structure of human anatomy. By using this framework, we turn a vague visual failure into highly specific, system-level actionable information.
Finally, Section 6, a general intelligence architecture.
What we've mapped out today extends far beyond simple image generation. Diffusion is actually a general architectural pattern for processing complex information. Look at the flow we've established. Inject controlled corruption. Learn the repair vector. Apply repeated correction. Arrive at a stable structure. This pattern demonstrates that intelligent systems do not necessarily need to construct truth from absolutely nothing. Instead, they can simply learn how to remove distortion from a partially corrupted state. Just imagine applying this to incomplete reasoning, uncertain planning, or noisy organizational memory. Picture a future where an AI doesn't just generate a picture of a cat, but ingests a completely chaotic, noisy corporate spreadsheet full of scattered data and iteratively denoises it into a highly coherent, stabilized business strategy. It's really about recovering structure from chaos, wherever that chaos exists. I want to leave you with this final thought. We've seen how diffusion models turn pure uncertainty into stunning, coherent forms, just by repeatedly stripping away the noise. The visible image is really only the final artifact. The true strategic asset is the denoising system itself. So, if intelligence is simply the repeated removal of distortion, where else in your industry could we apply this governed architecture to recover order from noise? Thank you so much for joining me on this explainer, and I hope this changes the way you view the systems that are building our future.